In this video, we want to talk a little bit about the costs of production. So in our previous video, we talked about production functions. We talked about the difference between a short-run production function and a long-run production function. And then we talked about that firm problem of minimizing cost, choosing the combination of labor and capital that is the least cost way of producing a particular level of output. What we want to do now is we want to go back to costs of production. We want to link production up with costs, and we're going to go back to thinking about kind of the short run. And the reason is that that's a little bit more simple. Let's review a few things that you would have learned in your principles class, but we need to make sure that we go back over them just a little bit here, and that is the difference between accounting cost versus economic cost. Accounting cost versus economic cost. So remember that when we're thinking about economics, we think about costs as including both implicit and explicit costs. If we were in an accounting class, we wouldn't be worried about implicit costs. We would only be thinking about explicit costs. So because we think about costs differently, we also think about profit differently. So we can think about accounting profit versus economic profit. Let's just write those out. Accounting profit is equal to total revenue minus explicit costs. But in this class, we're economists, and so we're going to be thinking about economic profit, and economic profit is total revenue minus explicit costs. I'm just going to say also minus implicit costs. That should be implicit. We don't want to ignore any cost because we want to understand firm behavior. And so, if we were thinking about just accounting in terms of keeping an accurate record of the dollars that go into and out of a business, it's only explicit costs that are important. In terms of behavior, we can't ignore any particular cost. Let's think about sunk costs. Let's just review a little bit about what we know about sunk costs. So a cost is sunk if it's already been committed and cannot be recovered. So a sunk cost is very different from an opportunity cost. An opportunity cost, the magnitude of it depends on the behavior that you engage in. But with a sunk cost, it's been based on a decision that's already been made and there's nothing you can do about it. So what we know is that sunk costs should not affect current or future decisions. Not useful for making decisions. And the reason is there's nothing you can do about them. If you make this decision, you still got to pay the sunk cost, and if you make that decision, you've still got to pay the sunk cost. So you need to ignore that decision ignore that cost in terms of making good decisions. And we know from our principles class that firms do indeed ignore their fixed costs, their sunk costs, when they make production decisions. So firms do not pay attention to any cost that's sunk, and for the firm, their fixed costs are sunk. So fixed costs are not useful for making production decisions. So let's just kind of review the costs and what we know about them from our principles classes. We can think about fixed costs, which we always abbreviate FC. Fixed costs do not depend on output. Do not depend on Q. We've got variable costs. Variable costs, not equals. Let's say variable costs do depend on Q. If output goes up, you've got to have more labor. And so the cost of labor is a variable cost. It goes up. And then we know that total cost is equal to fixed cost plus variable cost. Let's quickly review the average measures that you would use in a principles class. We'll use them in the exact same way. We know that average fixed cost is equal to fixed cost divided by Q. We know that average variable cost is equal to variable cost divided by Q. And we know that average total cost is equal to total cost divided by Q. And we can take this and we can make an average version of it. We know that average total cost is equal to average fixed cost plus average variable cost. So those are all things that you would have learned in a principles class. And you would have drawn pictures of those cost curves. You probably went through an example where you used some numbers and a production function to come up with some total cost numbers. But basically, what you would have ended up with is thinking about a picture of kind of the average cost curves. And the average cost curves look like this. We've got rising marginal cost. I'm going to put costs up here, put quantity down here. We've got rising marginal cost. We have a U-shaped average total cost and a U-shaped average variable cost. Our marginal cost comes up through the bottom of both of these average cost curves. So that's kind of the picture of typical cost curves that you would use in a principles class. We're also going to use them in this class. So everything that goes behind those cost curves, you already know. If you need a refresher on that, you can go to YouTube and you can find my discussion of the costs of production from my Econ 1011 class. So if you want to go back and watch that, that might be a good thing to do to kind of brush up on what goes behind that picture that we're using there. What we want to do now is we want to go beyond what you would have done in a principles class, and we want to think about the difference between, say, the short-run total cost curve and the long-run total cost curve. We saw what the long-run total cost curve looked like. We want to compare that to what a short-run total cost curve looks like. So let's think about this capital labor picture that we developed in our previous video. So we've got labor down here, we've got capital up here. Let's go back and look at that expansion path that we put together in the end of the previous video that we went through. So let's suppose that we wanted to produce 10 units of output, quantity equal to 10. We saw that the relative wage is going to determine the slope of the isocost line. And so once we know the relative wage, then we can look and see where the isocost line is just tangent to that isoquant. And let's suppose that happens right here. I'm going to go ahead and extend that down to that horizontal axis. We called this, I think, X. And we had a cost associated with that. I think it was $100. It's not important to know the number right now. But we were able to use this intercept to figure out the cost of production because we know that this intercept, whatever it is going to be C divided by the wage rate. So if you know the wage rate and you know this intercept, then you can easily figure out what the cost of production is. So for example, if the intercept was, say, 200, so if you look at the horizontal scale and this is 200, then you know that 200 is equal to C divided by W. Well, if the wage is $2, if wage is equal to $2, then you know the cost has to be equal to 100. So we've got X here. Then what we did is we said, okay, let's think about the cost of production if we wanted to produce 20 units. And we said, okay, now we need to figure out where that isocost line is just tangent here, and that happens someplace like this. We called that Y, and then we did it again for a quantity of 30. We found where that isocost line is just tangent. That's someplace like there. We called that Z. And we could use the horizontal intercepts of each of these to figure out the cost of production that would correspond to those other isocost lines. And then what we did was we connected those to get the expansion path, something like that. Then we pulled off some numbers from this picture, the quantity numbers and the total cost numbers, and we drew the long-run total cost curve. What I want to do now is think about what the short-run total cost curve would look like. So to do that, let's, I don't know if this will show up as a different color very much, but let's do this. Let's suppose that we think about what would happen if we had a fixed amount of capital. In this picture, we're able to choose whatever quantity of capital we want, but we know that in the short run, the quantity of capital is fixed. So let's fix the quantity of capital let's say right here. K bar. There's the fixed quantity of capital. And that means that no matter what amount of labor we choose to use, we always have to have this amount of capital. Now let's think about that line that I've just drawn. We saw in our previous video that this line that connects the origin and X and Y and Z, this line is what we would call the long-run expansion path. What's happening there is that we're able to adjust the amount of labor and the amount of capital. We're using a different combination of labor and capital here than what we're using here, than what we're using there. But now, once we've chosen the level of capital, then we're stuck with that level of capital. We're stuck with it in the short run. And so this blue line that I have drawn, this is what we would call the short run expansion path. What it tells us is the amount of capital that we have to use. Now I'm going to extend this isoquant up here so that we can see what now the combination of labor and capital that we're going to use to produce 10 units, 20 units, and 30 units. So let's suppose that we want to produce 10 units of output. If we want to produce 10 units of output, we're stuck with this amount of capital. So the combination of labor and capital that we're going to use to produce 10 units of output is going to be right there because we don't have any flexibility in terms of capital. So if we draw the isocost line through this point, it's going to be parallel to the rest of them, and it's going to be right there. Notice that the difference between this isocost line and this isocost line tells us the cost difference between being able to choose the right amount of capital versus being stuck using this amount of capital. So you would be able to use the intercept of this isocost line right there to figure out how much more costly it is to produce 10 units of output in the short run with this amount of capital than it could be if we used the optimal amount of capital. So we can see that to produce 10 units of output in the short run is more expensive than to produce 10 units of output in the long run by optimally adjusting capital. Now let's think about what would happen if we wanted to produce 20 units of output. Well, if we wanted to produce 20 units of output and we could adjust capital and labor however we wanted, we would produce right here at point Y. But if we're stuck using this amount of capital, then right here is going to be the combination of labor and capital that we use because we can't adjust capital. So what we have to do is find the point on that isoquant for 20 units of output that corresponds to the amount of capital that we've got. And we would use this amount of labor. Let's call this point Y prime to distinguish it from Y. Let's actually call this point X prime to distinguish it from X. Now notice that it's going to be more expensive in the short run to produce 20 units of output, but not as much as it was down here. So if we look at the isocost line through point Y prime, we see that it's on a higher isocost line, but not as much higher than it was down here. Okay. Now let's go up here to produce 30 units of output. Now notice that when we look at the point right here, 30 units of output, we're going to use this point Z prime, which isn't that far away from Z. So if I draw the isocost line through point Z prime, it's going to be just a hair above the isocost line through point Z. So you can see that to produce 30 units of output, we've got almost the right amount of capital. Not quite, but almost. And so since we have almost the right amount of capital, it's not that much more costly to produce 30 units of output in the short run than it would be in the long run. So you can see it depends on how close we get to the right amount of capital in terms of how much more costly it is. If we were to produce 40 units of output or 50 units of output, then we'd be getting farther away from the right amount of capital. And our isocost lines would start getting farther away from the optimal isocost line. So now if we took the information from this picture in terms of x prime, y prime, and z prime, we could create the short run total cost curve. Let's draw a quick picture of that. It's actually very easy to do. So I'm going to draw the short run. Let's start with the long run total cost curve. So remember, we've got costs up here. Let's move that over. We've got costs up here, and we've got quantity down here. And our long run total cost curve that corresponded to x, y, and z came out of the origin, and it looked like that. There's our long run total cost curve. Our short run total cost curve, notice that because we've got a fixed input, we are going to have a fixed cost. So if we reduce output to 0, we still have to pay for this capital that we've got. That means that our intercept of our short run total cost curve is going to be up here higher than the origin. But notice that as we increase output, it's at first much more costly, and then as it's the distance between the two isocost lines is big, but as we move closer to this quantity of 30 units, it becomes less and less costly. But then as we move past 30, it's going to become more and more costly. What that means is, let me do the short run total cost curve in a different color. It's going to be above the long run total cost curve, but as we get closer to a quantity of 30 out here, it's going to get closer and closer, and it's going to touch that long run total cost curve in one place right there around 30. It's not going to be exactly at 30. It's going to be a little less than 30, it looks like. So somewhere right in here, and then it's going to head up like that. This is going to be the short run total cost curve. It lies always above the long run total cost curve, but it does touch in one place because there is one quantity of output for which K bar would be the optimal quantity of output to be producing. And that point would happen right there where those two total cost curves touch each other. So this gives you hopefully an idea of how the long run total cost curve and the short run total cost curve are related, and how you would take this expansion path picture and get the short run total cost curve numbers from it. Your quantities would come from the isoquants, and the cost numbers would come from this intercept down here, and knowing what the wage is. So I need to clear this off, and then we'll take a look at some economies of scale and diseconomies of scale and a couple of other things. Let's take a look at how the average total cost curves relate to each other in the short run and the long run. And this is something that you would have seen in a principles class, but I think it's useful to kind of review it in this class as well. So let's think about our quantity down here, and we'll put costs up here. If we think about long-run average total cost versus short-run average total cost. And we're thinking about average total cost here, so it's going to be U-shaped. We can think about the average total cost curve for a small plant, so we'll call that short-run average total cost for, I'll just write the word small here, for a small plant. We could think about the short-run average total cost curve for a medium plant. I'm going to draw it a little bit lower. So there's short-run average total cost for a medium plant. Just write medium. And then we could think about the short-run average total cost curve for a large plant. And I'm going to put it over here. Here's short-run average total cost. I'll just write large. Now we could draw in all of the infinite number of plant sizes, and if we did that, this would end up being one big blue bowl-shaped area. And if we were to take and kind of draw in the lower surface or frontier of that big bowl-shaped area, it would look something like this. And that's what we call the long-run average total cost curve. So the short-run average total cost curve, all short-run average total cost curves lie on or above the long-run average total cost curve. And that's related to the picture that we had right over here just a second ago, where we had the total cost curve, and we saw that total costs in the short run were everywhere above total costs in the long run except at one point. Well, this is a very similar idea. You can't do better in the short run than you can in the long run, because in the long run nothing is fixed. In the short run something is fixed, and that leads to a constraint on you that prohibits you from doing any better than what you could do in the long run. So this is our long run average total cost curve. Let's talk about economies of scale. So previous video we talked about returns to scale. That tells us something about the relationship between inputs and output. Now we're going to think about economies of scale. That tells us something about the relationship between output and the costs of production on average. So I'm going to draw another long run average total cost curve, and let's just review here. I'm going to draw it kind of with a flat portion here like that. It's decreasing. Here's costs, here's quantity down here. Average total costs are decreasing as we increase quantity up to somewhere right in here. And then they're constant for a while, and then they start to go back up somewhere right over in there. And we know that the firm experiences economies of scale right in here. Here's constant returns to scale. And then over here, this is diseconomies of scale. So let me give you the definition for economies and diseconomies of scale. And we can think about it in terms of doubling output and what that does to your costs. So you've got, let's say, constant economies of scale if doubling output doubles your costs. You have economies of scale if doubling output less than doubles your cost. And you have diseconomies of scale if doubling output more than doubles your cost. Okay. Now, if you go back and you think about what causes economies of scale and diseconomies of scale, remember that doesn't have anything to do with the law of diminishing marginal product. Remember, economies of scale comes from the fact that a bigger production process allows your workers to specialize. And as they specialize, they become more efficient, so your costs go down on average. Diseconomies of scale is a result of the fact that really large production processes are hard to manage. You have to hire additional layers of management, and that drives your costs up on average. Let's make sure that you remember that this is a long-run average total cost curve that we've got there. Okay? let's talk about something that you haven't discussed before, and that is economies of scope. So let's think about what that means. Economies of scope. Economies of scope tells us something about how a firm's costs change when they produce multiple products. So most firms produce more than one product. They might produce 2 products or 20 products. We'll think about 2. So let's consider a firm that produces 2 goods. So we could think about a total cost curve, and that total cost curve would be a function of the amount of good 1 and the amount of good 2. And if you're not sure what I mean by a total cost curve, I'll give you an example here in just a second. But for now, let's keep it general. Suppose we have a function of the amount of good 1 and the amount of good 2. Then a firm is going to experience economies of scope if this is true. So a firm experiences economies of scope if the total cost of producing the 2 goods together is less than the total cost of producing the 2 goods in individual production processes. So let's write out what that means. The total cost of producing the 2 goods together is less than the total cost of producing good 1 in one facility and none of good 2, plus the total cost of producing good 2, none of good 1, producing good 2 in its own facility. So this is the total cost of producing good 1 by itself. Here's the total cost of producing good 2 by itself. So you could set up 2 production processes, one facility that produces only good 1, one facility that produces only good 2. But if the total cost of producing them together in one facility is less than the total cost of producing them individually, the firm is experiencing economies of scope. The idea here is that there's a benefit to increasing the scope of your production process, not the scale of it. The scale refers to how much of one good you're producing, a little or a lot. We're talking about producing multiple goods here. So if you produce multiple goods, is it more expensive to produce them together or more expensive to produce them individually? And your book is going to create a measure that they call scope. I think it's pretty easy to understand with this. And again, I'm going to show you what this means here in just a second. So if you're not sure how to operationalize this, I'll show it to you here in just a second. But your book is also going to create a measure that they call scope. And it looks like this. Scope is the sum of the total cost of producing good 1 by itself and no good 2, plus the total cost of producing good 2 by itself and no good 1, minus the total cost of producing them together, Q1, Q2. All of that divided by the total cost of producing them together. So if scope is positive, let's think about what that means. If scope is positive, then that means the total cost of producing them individually is bigger than the cost of producing them together, and the top would be positive. If this term is bigger than that term, our numerator would be positive. Of course, the total cost of producing them together is positive. So if scope is positive, scope greater than 0, then there are economies of scope. If scope is exactly equal to 0, there are no economies. If scope is negative, there are diseconomies. So if scope is less than 0, there are diseconomies of scope. let's think about this one. If scope is 0 or is negative, then that means that the cost of producing them together is bigger than the cost of producing them individually. And so you take this number, subtract off that number, and this, since this number is bigger, it turns the whole thing negative. So let me give you an example of a cost function. So we've talked this video, we talked about fixed cost, variable cost, we've talked about total cost in terms of economies of scope, but let me give you kind of an idea using some specific cost curves as to what these things are going to look like. Let's start with a firm that produces only one good. Let's suppose we had a total cost curve that looked like this. Total cost is equal to 100 plus 3Q. So there's a total cost curve. We would write it in general form this way. Total cost is a function of Q. Okay? It depends on how many units of output that we're producing. So there's our total cost curve. Notice that the definition of a fixed cost is a cost that doesn't depend on Q. This term right here doesn't depend on Q. This is fixed cost. The definition of a variable cost is a cost that does depend on Q. That one has Q in it. That is our variable cost. So you can see that total cost is equal to the portion that is fixed plus the portion that depends on Q. Total cost equals fixed cost plus variable cost. So if we wanted to know the total cost of producing 2 units, then it would be 100 plus 3 times 2, which is equal to 6. It would be $106. Or if we wanted to know the total cost of producing, say, 4 units, then we just plug in 4 for Q. It would be 100 plus 12. It would be $112. So if you know the cost function and I were to give you a quantity, you could easily plug that in and figure out what your total cost of production is. We could divide this by Q. So if we've got total cost equal to 100 plus 3Q, then I could figure out average total cost by dividing by Q. Well, if I divide by Q over here, then total cost divided by Q is average total cost. I'm going to get this. Average total cost is equal to 100 over Q plus 3Q over Q. Well, over here, this 3Q and that Q down at the bottom, they're going to cancel. It's going to leave me with just 3. Notice that this term, 100 divided by Q, that's average fixed cost. This is average variable cost. All right? So we see that average total cost, that should be average total cost. That should be a C. Average total cost is equal to average fixed cost plus average variable cost. So if I were to give you a cost curve, you could easily figure out what portion of it was the fixed cost, what portion of it was the variable cost. You could use your definitions of your average total cost and average fixed cost and average variable cost to figure out what they looked like. Average fixed cost is 100 divided by Q. Average variable cost is just 3. Let's talk about what these cost curves would look like if we were thinking about a cost function, a cost curve, that was a function of 2 different quantities. So here, it's a little more complicated, but not much. Here our total cost, which is a function, let's say, of Q1 and Q2, could be something like this. It could be, say, 500 plus, let's say, 10 Q1 plus 20 Q2 minus 3 Q1 times Q2. Now that looks complicated, but it's actually not. It's very simple. All you would need to do, if I were to tell you to give me the total cost of, say, 2 units of Q1 and 5 units of Q2, you'd just plug in everywhere there's a Q1, you'd plug in a 2. and everywhere there's a Q2, you'd plug in a 5 there and there, and you could easily figure out what your total cost is. In terms of how to figure out this stuff, well, this term right here means that if we're thinking about total cost of producing a particular quantity of Q1 and no Q2, then everywhere there's a Q2, you would plug in a 0. So let's suppose that I said, let's do this economies of scope thing. Let's figure out this term using these numbers. Well, that means we're going to figure out the total cost of producing 2 units of Q1 and 0 units of Q2. That would be this term. Okay? That means that we're going to have the 500 plus 10 Q1. Well, Q1 is 2, so we're going to have plus 10 times 2. For this term, it's just going to fall out because Q2 is 0. And so that term's going to fall out. Also, this term's going to fall out because Q2 is 0. So the total cost of producing 2 units of Q1 and no units of Q2 is going to be $520. So these terms are easy to figure out. In this one, you would just plug in a 0 for Q1, and then whatever your Q2 is, 5. Okay? So figuring out scope is not challenging. You just plug in the appropriate things, and wherever you have a 0, just plug in a 0 for that. So that hopefully gives you an idea of what costs look like. You can see that this is very, very similar to what we did in a Principles of Micro class. What we're going to do in our next chapters is we're going to use this to figure out how perfectly competitive firms maximize profit, how monopolies maximize profit, monopolistically competitive firms, oligopolies. So I'll see you in a future video.